episode, we will take up the origin and success of quantum mechanics. The lecture has been planned in such a fashion that we will try to recall what we did in previous lectures. Thereafter, we will take up the meaning of quantization and see how does it explain the blackbody radiation problem. Thereafter, we will see that this concept of quantization can be used successfully in explaining the other phenomenon which could not be explained in terms of classical theory, that is the photoelectric effect, the anomalous heat capacity of solids, atomic spectra and Compton scattering. And towards the end, we will try to summarize what we do it in this episode. Let us try to recall what we did in the previous lectures. We broadly did three things. First, we discussed the premise of our classical mechanics and saw that how successful was it in explaining macroscopic phenomenon. Thereafter, we took number of examples, so 5 different cases wherein we show that the inadequacy of classical mechanics to explain the results of those experiments. And in the process, we established the need of a new theory to explain these results. Now, this so-called new theory happens to be the theory of quantization or the origin of quantum mechanics, so to say. What happened was this concept of quantization came into being, to be specific, on December the 14th, 1900. That is the day on which Max Planck proposed his present explanation for blackbody radiation in terms of this concept of quantization, and that is the day the quantum mechanics was born. And what he did propose, let us try to understand that. The basic presumptions or the assumptions of Planck's explanation was that the energy of oscillators, that is the blackbody we are talking about, that is made up that atoms and molecules are acting as oscillators. Planck proposed was that these oscillators can take up only discrete values. The classical theory predicts that it can take up any value. As against that, Planck proposed that it can have only discrete values. That means the energy happens to be quantized. What it means is the following, that is the oscillators can have energy given by, say, En is equal to nh nu, where nu is the frequency of oscillator, h is the new constant which now is known as the Planck's constant, which was introduced by him. Say for n is equal to 1, when n is equal to 1, then the oscillator energy will be just h nu, nu is the frequency. N is equal to 2, it will be 2h nu, 3h nu, 4h nu, 5h nu. That means it can take only certain multiples of that. That is the meaning of quantization. Contrast this with what we had in case of classical mechanics. Energy can take up any value. These discrete values of energy, they correspond to different quantum states. So, this is first state, second state and so on and so forth. Let us try to understand the meaning of this quantization. Let us look at this small animation. This is 1, 2. So, what do we see in this case is, say we have an incline here, inclined plane, and suppose this is an object here. This object slides down the incline. As it is coming down, let us look at the potential energy of this particular object. It has certain potential energy when it is at the top of this. As it comes down, it can take up any potential energy possible depending on the height. As contrast to this, what we have is, in this case, the system can have potential energy of this level or this or this or this, nothing in between. So, that is quantization, this is continuous, this is classical behavior, this is quantum mechanical behavior. That is what exactly is the proposition of Max Planck. Let us take another example. We know the currency. Currency is quantized, say 5 rupee, 10 rupee, 20 rupee, 50 rupee and so on and so forth. You do not have a currency note of say 5.7 rupees. So, that means all this currency is quantized, it can take up only certain values, not all possible values. So, that is the basic meaning of quantization. So, that is the proposition of Max Planck. Having done that, what he further said was these oscillators which are kind of constituting the blackbody, they are in different states. So, when they go from one state to another state, suppose they are say lower state, they take up some energy, go to higher state, or if they are at higher state, they can come down giving out the energy. So, that means the energy absorption or emission is accompanied by change in the state of the system. And thirdly, when this transition takes place, when the energy comes out, that is absorbed or emitted, it will be in terms of packets. Suppose I have say a quantum state 3 is there, say n is equal to 3h nu. From there, if I come to second one, so that the difference will be emitted out as energy. That will be a packet over there. That's the 3 assumptions or the 3 propositions of Max Planck. On the basis of these propositions, what Planck did was he formulated the following expression, and this expression was in exact agreement vis-a-vis the experimental observations of blackbody radiation. If you remember, in the classical case, there were two things. Wien's proposition kind of agreed for low wavelength region, and Rayleigh's agreed for the higher wavelength region, whereas the Max Planck description of blackbody phenomenon agreed with the whole range. There was an excellent agreement between the theory and experiment. So, that is the triumph, or that is the proposition of quantum mechanical, or this concept of quantization, so to say. Now, having done this, as I just said that the predictions matched exactly with the experiment. It could be even seen that the Planck's formulation can be reduced to either Wien's formulation or to Rayleigh's, depending on the limiting cases. So, low wavelength range, it will bring down to Wien's formulation. At high wavelength range, it will match the Rayleigh's formulation. So, it gives you a general description of blackbody radiation. Now, having done this, let us see how do we use this concept of quantization, how was it used. The next best use came in 1905 by a person nothing short of Albert Einstein, who used this concept. Basically, what happens is, when you talk about quantization in the context of blackbody radiation, Max Planck said the energy is quantized. Contrast from there, what Einstein did was, he extended this concept of the quantization to the radiation, the light. So, what it said was that this light is not continuous, because classically speaking, light you visualize as a wave, that is continuous, the energy is spread over the whole wave. As against that, Einstein said the energy of light is not in the form of a wave, it is made up of particles or packets of energy called as quanta. Singular is called as quantum, and each packet of energy carried by the wave has energy equal to h nu, depending on the frequency of the radiation I am talking about. Nowadays, these light quanta are called as photons. This was given by G. N. Lewis. This term was coined much later than, because initially the term was quantum or quanta in plural, and later on now it is called as photons. That is a widely used term now. So, now let us try to see if we have got this perception or this visualization of our radiation or light, how does it explain our photoelectric effect? See how beautifully we can do that. The rationale here is, you visualize that light is coming as stream of photons, packets of energy. Okay. So, when this light falls on the metal, these packets of energy, they strike the electron, and when they strike the electron in the metal is held by the forces, neighboring forces, by the cations and other species over there. And when you give energy to that energy knocks off the electron from the metal, and what you have is photoelectric effect coming, or electricity coming out of that. So, that is the way we visualize that. What happens is, since I am talking about packets of energy, when the packets of energy coming there, so what Einstein visualized was that in the metal you got electrons, this packet of energy comes, hits the electron. So, the moment the packet of energy, the photon hits the electron, the energy is transferred, and immediately if energy is sufficient, electron will be knocked off. So, there is no time lag, and that is what exactly was experimentally observed, but classical theory tells us there has to be time lag. So, we contrast here that this quantization concept makes this agree with the experimental observation. Secondly, you can see that if I give a photon, say light radiation of low frequency, that means the frequency is low, means energy is low, that means the packets are of very small amount of energy, they may not be sufficient to knock off the electron, electron will not come out as experimentally observed, till such time that I use a radiation having a reasonable amount of energy. That means the frequency is having certain value of say nu naught, what is called as a threshold frequency. That means if my radiation has frequency less than that frequency, the electron will not be coming out, and that is what exactly was experimentally observed. Whereas our classical theory says that there is no need of a threshold frequency, no matter what frequency you use, electron will come out sooner or later, but that is not the case. So, our experiment and theory are exactly in agreement with each other as per Einstein's proposition. Okay. So, what we have is this h nu gives me the energy of the photon which is being shown on the metal. Out of that, part of the energy, that is h nu naught, is used to knock off the electron, and rest comes out as the kinetic energy of the electron. According to Planck, it means higher intensity means I am giving more number of photons. When I am giving more number of photons, and since each photon is going to strike an electron and knock it off, so more photon means there will be more electrons coming out. And the kinetic energy of electrons will depend only on the energy of a photon, that packet, depending on the strength. Suppose as a given packet is there, so that packet hits the electron, knocks it off, the electron comes out with certain amount of energy. Okay. So, as all packets are of the same energy, so all electrons will come out with the same kinetic energy. So, that again explains our all observations of photoelectric effect are fully well explained in terms of our the concept of quantization as proposed by Einstein, quantization of radiation. Okay. So, what we see is that this concept of quantization is able to explain two experiments fairly well, which were not possible classically speaking, the Blackbody radiation and now the photoelectric effect. Let us go on to the next one. Next one, if you remember that in case of heat capacity of solids, the Dulong particle law says at room temperature the specific heat and the atomic mass, the product of the two is equal to constant. And we found that at low temperatures there was a deviation from that, and that could not be explained classically. What Einstein said was that the atom in the solid, that is the heat capacity solid I am talking about, the solid that behaves as a three-dimensional oscillator, harmonic oscillator, is oscillating in harmonic fashion. And what he said was that these oscillators oscillate independent of each other. And then thereafter the third thing proposition was that all the oscillators oscillate at the same frequency. On the basis of these three assumptions, he gave a formula and which did explain first the two things that explained was, first, that there is a good agreement vis-a-vis the experimental observation at high temperatures or moderate temperatures. And further, it did account for decrease in the heat capacity of solids as temperature goes down. However, the decrease as suggested by Planck was much steeper than what was experimentally observed. So, there is a partial success in this case. The partial success probably because the assumptions were not in order, and this partial success was improved further by Debye in 1912. What Debye said was that as assumed by Einstein that oscillators are independent of each other, he said they are not independent, they are coupled. That means oscillation of a given oscillator will influence that of the neighboring oscillator. That is one thing. And secondly, they all do not oscillate at the same frequency, there is a spread of frequencies over there. And on that basis, the formula which was given by Debye agreed exceptionally well with the experimental observations. What we see is that in this short span of about 12 years, three important experiments whose results could not be explained on the basis of classical mechanics have been explained exceptionally well by invoking the concept of quantization. Now, and that means this concept is here to stay. Let us see how does this explain our fourth challenge to classical mechanics, that is the origin of atomic line spectra. You remember that when we talked in the previous episodes, we talked about that heated elements or atoms will give radiations which are which form a spectrum which is a line spectra. It is discrete lines are coming over there as against a continuous spectrum. To answer this question, the origin of line spectra, Niels Bohr proposed in 1913 the model for an atom, and he proposed the model for hydrogen atom. And what he did was, he did a very judicious and smart mix of few things. What he did was, he took the concept of quantization from Max Planck, used the idea of photon as given by Einstein, and then used Rutherford's model of an atom wherein there is a nucleus in the center, electron is outside that, and then use a little of Newtonian mechanics, that is a classical mechanics, and added a few things on his own. On this basis, he gave a recipe, a kind of a formulation or a model for an atom which explained the hydrogen spectrum fairly well. Let us see what is the model and how does it explain our observations. The Bohr's model can be understood in terms of the four broad postulates. Let us understand what are these postulates. the first postulate states that the electrons move in a definite circular path around the nucleus. So, what we have is, you have a nucleus and the electron is moving around the nucleus in a circular path. Contrast this with what Rutherford said. Rutherford said it is moving and then it just moves. But in this case, what we are talking about is, I think almost similar to what Rutherford said, that it is moving in a circular path, but the distinction comes in over there in terms of that it cannot have any path, it can take up only certain paths. That means only certain electron orbits are stable or allowed. That means the electron can be outside the nucleus in some of the allowed orbits. It can't be at any distance it wishes to be. It can be allowed only to be at certain distances or so called energy orbits. And the energy of these orbits is given by, again, quantization. It is quantized in terms of a quantum number called as n. And what it says is, energy is given by minus RH1 by n square, where n happens to be an integer, positive integer 1, 2, 3. He said that as long as the electron is in a given orbit, it will not radiate, it will not give out any energy. That means, he said what is called as a stationary state. Now, this is it is in contrast to what is the expectation on the basis of our Maxwell theory of electromagnetism, because according to that theory, the electron must radiate if it is accelerating around the nucleus. But Bohr said for whatever reasons that this is not going to radiate. It's a bold proposition, but we feel satisfied because it does explains our experimental observations of hydrogen atom spectrum, though we have things going beyond that now. Now, the third postulate is that when the electron is in different orbits around the nucleus, different energy levels is there. So, it can go from one level to another by absorbing radiation, or it comes from a higher level to a lower level by emitting that difference in energy outside as a photon. Okay. We can visualize that in the following way. So, what we have is, do we have a nucleus and there are different orbits in which electron can reside. And what we have is, suppose the electron is in this particular level. If I give a photon to that, the electron captures that energy, absorbs that energy and moves on to a higher energy level here. This is called as absorption. Opposite to that, suppose the electron happens to be in higher energy level. It can come down to a lower energy level, and this difference in energy it emits as a photon. So, absorption and emission are accompanied by changes in energy levels. Essentially, this part of it, that is the electron coming from higher energy levels to lower energy level, accounts for the so called line spectrum of hydrogen atom, because what we had was different series of lines there. These lines come because electrons from higher level are coming to lower level and then giving out fixed packets of energy. So, we have got only discrete wavelengths coming over there and not a continuous spectrum. The fourth postulate talks about what is called as, it gives you some idea about a size, that it can take up only certain orbits wherein the electron's angular momentum happens to be quantized again. That means, the angular momentum, that is MVR of the electron in a given orbit will be equal to n times h by 2 pi. H by 2 pi is now called as h cross, is called as action constant. But basically, this postulate says is that the angular momentum also is quantized. So, if you look at closely, this also gives you an idea about the size of the orbit. Now, let us see on the basis of these four postulates, what do we get out of here? What we get from here is, we are not getting into mathematics of that, but what we can see is the results part of it. What we see that using Bohr's postulates, we can derive an expression for Rn. Rn is the radius of nth orbit, and what you find is these all are constants over there, h square by 4 pi square me e4, and then this you have is an integer n square. So, what you find is that is a radius of the orbit is quantized. We can put it like this, say Rn is equal to n square a naught, where a naught is called as a Bohr's radius. When your n is equal to 1 means you are at the first level from the nucleus. When n is equal to 1, that radius is now called as Bohr's radius, just to kind of recognize his contribution. Okay. So, and this value happens to be for hydrogen atom is about 0.0529 nanometer or 0.529 angstrom or 52.9 picometer, different ways of representing the same thing. So, that is my Bohr's radius, that is the first orbit. when n is equal to 2, Rn becomes 4 times A naught, third will be at 9 times, next will be 16 times. So, what you find is that the nucleus is right in center, the energy levels are 1 here, third one, fourth, and then the distance goes on increasing as a square of the quantum number. This formulation of Bohr also gives you an expression and for energy of that, and what you find here is that En is equal to minus of 2 pi square me e 4 n square h square. What is important is that all these terms here are constants other than the n, and show that En to be equal to minus of Rh by into 1 by n square. That means there is proportional inversely to the square of the quantum number. What does it mean? Two things we have to understand here. This is very, very important. And before I come to that, one must also appreciate that there are three things. One is you get a value Rh. This is called as a Rydberg constant. This is the expression, the value of that. If you put all the constants in this, you get a value which is exactly what we got empirically from the experiments done much earlier than this theory came up. So, what you find is there is an excellent agreement between the theory and the experiment. Now, this value is negative. Let us understand the meaning of negative means. Now, we have a nucleus and electron is at the first orbit over there. Now, why should this energy should be negative? It has to have some positive energy over there. The negative implies the following. Now, suppose you have a nucleus and electron is farther apart, somewhere around, say, at infinity. So, this electron at infinity and this nucleus over here, there is no interaction, there is no Coulombic interaction, the interaction energy is 0. As the electron comes closer and closer and comes closer and closer, reaches this first orbit, that means some kind of a stabilization is coming up there, that means energy is decreasing. Okay. So, when it comes to this particular level, say n is equal to 1, this has an energy of say about minus 13.6 electron volt. So, that is a kind of stabilization the electron acquires by coming from infinity to my orbit number 1. That is why it is negative. Now, the third thing, the energy E2 is more than energy E1, because this will come out 13.6 by 4, that is about 3.4. Okay. So, it is minus 3.4 here, minus 13.6. So, this is positive by the rest of the amount, that difference of the two. Okay. So, as we go away from the nucleus, the energy of the orbit goes on increasing. Okay. So, that is the three things we have to be very clear about. So, this energy expression what we get from Bohr's model, that actually can be used to drive an expression for the change in energy when an electron goes from comes from higher level to lower level. So, what exactly we observe in case of the spectra, and what you find is this expression is exactly the same as what was experimentally observed when we had that Raman series, Balmer series and so on and so forth. So, we find that there is an excellent agreement between the two again. Now, this is just to a graphical representation of the same thing. Say Balmer series. Balmer series is when the electron is coming from level number 3 to 2, 4 to 2, 5 to 2, 6 to 2 and so on and so forth. That means electrons starting from any level other than higher than level number 2 and comes down to level number 2. So, that actually falls in the visible range, and that is what is the Balmer series, what was experimentally observed. So, we find is there is an excellent agreement between the experimental results. Let us try to see what have we achieved in terms of Bohr's model. One, we have been able to account for the stability of atom. Our Rutherford model was unstable because it couldn't answer why should the electron not lose energy as it should be spiraling around in the nucleus. And second thing is it did account fairly well for the spectrum of hydrogen atom. So, that is a positive part of it. But where did it falter was that if I go for atoms bigger than hydrogen atom, say helium atom and beyond that, we find it does not work out. It does not explain fairly well, there is something missing over there. Thirdly, what you find is these so called lines in the spectrum what got there they actually were not single lines, there was some fine structure in that. Even that fine structure could not be explained by Bohr. That was second inadequacy of Bohr's model. And thirdly, what we found is that this spectra what you get for hydrogen atom, if I do it under say the influence of magnetic field or electrical field, we find that there are more lines than what we observe. That is typically called as the Zeeman and Stark effects. Now, this also could not be explained in terms of Bohr's model. So, we find that Bohr's model was partial success, because it does explain hydrogen atom fairly well. To that extent, yes, but for other things it was not adequate enough. Now, let us take the fifth experiment we had given as a challenge to classical mechanics, that is Compton's effect. Compton effect also can be explained simply by visualizing the scattering of X-rays from the element, say nickel or silver or whatever, is just as a consequence of some kind of a collision between the photon, which is coming from light, and the electron in the metal there. Okay. So, when this happens, so this is a some kind of a billiard ball kind of a collision. That means there is an electron there, photon comes, strikes it. When it strikes it, what the assumption we have here is that the photons and electrons collision happens to be elastic in nature. What is elastic collision? Elastic collision means that in this process of collision there is energy exchange. But also the third thing we have here is, that is, the energy and the momentum of the photon is conserved in the process. Let us try to understand that picture here. So, what we have is, we have an electron here. You are giving a photon of a certain frequency or certain wavelength. The photon comes, has certain amount of energy or momentum with it. When this photon with certain amount of momentum comes, strikes this, there is a elastic collision. In this process, part of the energy goes to the electron, which recoils, and the photon gets diffracted away or scattered away. And when this photon comes now, it has energy lesser than that of the incident photon. As a consequence, this has a higher wavelength than that of this particular photon. So, this is what exactly was experimentally observed by Compton. And in terms of Compton's equation, that is delta lambda is equal to lambda minus lambda naught, so on and so forth. This means is the shift in wavelength as derived from this basis is in exact agreement with what we have experimentally observed. So, what do we conclude from all these arguments of ours? We conclude the following, that is, the quantum theory proposed to explain the experimental results of blackbody radiation has met with success in many other cases. We have seen 4 more cases there. Secondly, when we say that the concept of quantization has been accepted, because it is accepted because it is able to explain what we want to explain. So, having done this, let us try to quickly sum up what we have done today. Firstly, we discussed the concept of quantization as proposed by Max Planck to explain blackbody radiation problem. And then we showed that how this concept of quantization was extended by Einstein to the quantization of radiation, so as to account for photoelectric effect. And thereafter, we outlined the approaches of Einstein and Debye to explain the anomalous behavior of heat capacitive solids at low temperatures. Explained Bohr's model of atom and its success in explaining the origin of line spectrum of hydrogen atom. Having done that, we went further to explaining the Compton's X-ray scattering in terms of elastic collision between the photon and the electron, that is, photons of radiation and the electrons in the metal. And towards and on the basis of all this, we in the process of all this, we have been able to establish that the concepts of quantization of energy and radiation could explain the macroscopic phenomenon that could not be explained by classical mechanics. In the next episode, we will take up the issues of wave particle dualism and uncertainty principle. So, these two are very crucial for getting on to the wave mechanical model as we want to eventually come out to be.